Good morning, everybody. Today I'm joined by David, SecondThread on YouTube. We will do a very short, or maybe not very short, series called Algo Talk. Maybe called that, maybe not. If you have any suggestions, let us know. Hi, David.
Hello.
And we will be discussing some random cool problems in each video. One video should already be on SecondThread's channel. Check that out. We talked about IOI problem from 10 years ago, 15 years ago, a very nice one, joining points, and some modification of it. And now we'll talk about problem parade. Interesting thing is David doesn't know this problem. It's not extremely difficult, at least. And you will see him just getting new ideas, possibly wrong ones. And I'm the author of this problem, and likely I know all possible approaches, and I will be able to say what is a good path towards the solution, what isn't. First, the statement of problem parade. You're given a bunch of points, and a bunch means exactly n equal to 3000. 3000 points, and you need to choose exactly, not smaller equal.
And samples sound interesting then, but okay.
Sample was cheated. Sample had only 10 points. N equal to 300,000 except for the sample test. You need to choose exactly k of them, and k is again just equal to 500. It's not a variable. You need to choose k points, and you need to do TSP on them optimally. To viewers, I will explain in a moment what is traveling salesman problem, but you need to find an optimal path through them, or cycle. Here likely, but I'm not sure about that, it's this. You need to start from one of those chosen points, visit each of them, get back to the first point, and the total distance must be the minimum possible for this set of points. And here it's very important that we don't need to take points that are close to each other. It's possible that maybe you can choose a set of points closer to each other and their path will be better than what you found out. Your task, given n points, is to choose k of them, then forget about any other points, and given those k points, you need to find optimal path from the first point through visiting every point, getting back to the first of them. You need to print this sequence of points. Is the statement clear?
Yeah, I think I understand what we're supposed to do. I don't have any immediate ideas. I've got a couple things that are running through my mind, but I'll let you explain what TSP means first.
Now we give David a few minutes to think about any ideas, and then we will together discuss them. And in this time, I will explain this traveling salesman problem in general, and what is any solution for it. We will do 2 to nth power times something, I think times n squared, where if you're given a bunch of points, you want to visit all of them, starting, let's say, from this point, point 1. Then you might try something like always going to the closest point. And from here, I don't know, maybe this is the closest. But this is not always optimal. It's a reasonable, greedy approach. It works in n squared, where for every point we try to go to the next one. Oh, and in this variation where we need to get back to the first point, we also need to do that. This is for sure not optimal. If segments are crossing, it means likely that you're doing something wrong. And this exponential solution is possible, where after a few points already visited, there is a bunch of points. If I did this, and maybe that, I don't know, then I can remember which points are visited. That will be a mask up to 2 to n. And what is the current vertex, v. And we can call that dp. dp of mask v is the smallest possible total distance covered if we visited those vertices already. We started in point number 1. We are currently in V. And from this, you can iterate over every next U, every next vertex U. Doesn't have to be the closest one. And we will move to dp of the same mask, but bitwise or 1 shifted by U. And here U. We will move like that, where we add to the total distance covered so far, we add this one. At the end, we have dp of full mask at every vertex, then we know shortest path to get from vertex 1 to every other vertex visiting all other vertices, and we need to consider the last edge going back to 1. And that's the standard approach. This is NP-hard problem. Nobody can solve it in polynomial time. But there are very good heuristics. For real data, not malicious data, even for 100,000 cities or points, coordinates, there are algorithms, there are heuristics good enough that they find an optimal solution. It's not very easy to even check if it's very difficult to check if something is an easy solution, but they use enough heuristics, like for sure we will not connect those 2 points because this would be better. That they provide a solution and a proof for that in the computation of that. Now that we know how to solve this problem in exponential complexity, because this solution is 2 to k power, if you choose any k points, let's see if David has any ideas how to choose points in such a way that it will be easier for us to solve TSP.
So I definitely don't have a full solution thought out, but I have a couple ideas, and maybe you can work with me to try and see which ones are good to go down. So my first thought, seeing these bounds, was let's try something randomized. The bounds feel like the sort of thing where if I were writing the problem, the only reason to make sure that they're big or make sure they're fixed for some reason is so that we can do some analysis of like the complexity, or of like the chance of getting it right maybe. My next idea was like, if we want to pick a bunch of points, if all of those points are in a line or like almost in a line, it seems pretty easy to find the shortest path. Like if you imagine like those 5 points in the middle, Camille, if you pick those 5,
maybe this and
yeah,
this.
sure. Yeah, sure.
Alternative would be those 4 points.
If you pick 4 that are like almost in a line, it seems like just like connecting them in the line and then going all the way back is probably just the best by a pretty large margin. The only time you might have an issue is if you have 2 points that are both very close to each other. But that seems like it would be harder to get wrong.
I think this should correctly solve the problem if we don't need to get back to the first vertex. So if that's a path, not a cycle. Because, well, I think I agree that this is optimal. And actually here I agree that this is optimal. I will try to show you something where... What about this? I will first draw a line. And now what if points are like this? I claim that if you start connecting like that and then get back to the first vertex, that's bad.
Because you could do a donut sort of thing.
Yeah, so do you see what is better here? What is the good order?
You could do A, B, D, F, E, C, A.
Exactly.
I see. So the line is not helpful really at all. All right.
It's a reasonable idea. What I can tell you is that the thing, randomization isn't a good idea.
It's not.
Yes, it's not. In particular, it's important here that it wasn't guaranteed that the input is random. So the input data, how the points look like, it can be malicious for you. Organizers created different drawings. I remember that it was a pain to create various tests because we didn't know what ideas participants will try. We have various shapes and groups of points, pairs of points close to each other, triples of points, all kinds of things. But yeah, let's keep investigating this line idea.
All right, sounds good. Well, if we have, I suppose maybe the next thing to consider beyond having a line would be having some sort of circle.
Mm-hmm.
If you have something that looks like a circle, then it's clear how to do it. But I don't know, circles seem like a hard thing to identify.
Yes, but it doesn't really need to be a circle. What is a bit less round than a circle, and it is for a set of points? A convex hull. A convex polygon.
Oh, sure. Yeah, convex hull. Definitely, because that's very easy to find the shortest path around.
I will tell you that this is optimal cycle for such a set of points. But what does it mean for the full problem?
Well, so I guess you said random wasn't the way to go, but let's break that just so I'm confident and I believe you. If you have a bunch of points, you're saying if we randomly pick a subset of 500, or if we randomly pick 50% of the points maybe, then chances are the convex hull will have very few points.
I will show you an example of such a test.
That would do it, yep. You're always going to have 3.
Almost no matter what you do, if you choose those points, for example, the convex hull will have size 3.
That's a very, very good test case.
And it was in the test data. I will tell you that even if points are random, then I hope I'm not saying something stupid. The expected size of the convex hull is of logarithm of n in 2 dimensions.
I guess that makes sense.
I think so,
but reasonable.
We're not going there, and the input isn't
Sure.
The input isn't random.
So random's not the way to go. All right.
But
well,
I will tell you that you're investigating reasonable ideas. That's for sure. The
sure,
line, this circle/convex thing, you're getting there.
That triangle sort of thing, the three-pointed figure, that kind of leads me down the path of whatever a convex hull is, we're going to need to, for that, if we're going to pick some convex shape, we would want all of the things along some line. Because if you pick anything else, then your convex hull automatically has very, very few points. So if you have a convex hull, you have to count multiple points along the same line. I guess that's just one thing to watch out for. Maybe a small implementation detail.
You mean points being collinear?
Yeah, you have to include multiple collinear points in your convex hull in order to get enough points.
For sure, it's good for our convenience now when coming up with solution to not to care about collinear points and then at the end think if that's an issue.
Sure. If we can get a convex hull that's big enough, we can just remove points until we have 500. So we just need to somehow find 500 or more. Could we do some sort of DP maybe? Oh, I guess bounds are big.
I guess that for this triangle you would want to do something on 2 sides of this triangle. If we aren't choosing anything from there, if we just choose a bunch of those points, then it seems easy to draw a shape, but that might be not convex. I will tell you some intuition why. I don't even know if this is possible to choose such a subset of 500 points that it will be convex, maybe. But even in this triangle, slightly concave shapes are also fine for us, right? If we have something like this, this is still a good cycle. This is optimal here.
Sure.
So let's forget about the idea of convex point, convex hull or convex polygon, and let's get back to the idea of a line.
So we want to get like a bunch of almost linear sections and then try and combine them maybe? That's very hand wavy. I have no idea how you'd actually go about doing something like that.
Combining, I think, would be very difficult. What if I tell you that it's possible to just choose one line, whatever that means?
Well, if you just choose one line, you're in trouble. You need at least two, right? If you
let's solve the problem of just finding optimal path. I walk from vertex 1, visiting everything else, not getting back to 1.
Okay.
Because then we will prove that later that it is optimal in this drawing we're seeing now to do A, B, C, D, E, F.
Sure. If it's almost a line.
This is good. If we don't need to get back. At the end we will fix the getting back. So
so if we pick like two lines that are far apart, we're going to have to cross twice. So we could go like up one line, come across, come down, and then go across again. We could kind of make like a big box if you have the left side and like the right side are two different lines.
That might work. Yeah.
Coming up with a line, like whatever a definition from a line is, still sounds a little bit tricky to me though, because, well, I guess I don't have a strong grasp on when traveling through the line in a straight, like going in order of the line, when that would be beneficial and when it wouldn't be.
I agree that this is a good concern to have. And for that, I will show you a proof of when those points are, why it's good to connect them in a path. And, for me to form a proof, I need to formally define what I'm doing. And I will tell you this. If there is a bunch of points, let's say that first one is x1, y1, x2, y2, and so on, then I want to just use the fact that xi is smaller than xi plus 1, yi smaller than the next y. Given this, for every I will prove that path is optimal.
So this is any monotonic chain.
Yes. And while you think about what this implies, I will tell you the proof that one of many MST algorithms starts from a vertex and always finds the closest vertex. And here, such an MST algorithm would always find just point, the second point, then third point, and so on in exactly this order. Because if everything is monotonic, then among remaining points, then the one closest at x's and y's is closest. So, and there is an obvious condition that MST is only better than optimal path. The example of it is if we are given such points, then MST is this, but this is not a valid path. The optimal path visiting everything might be more complicated, can be only longer, but we already found with MST some answer using this, and this is also a good path, visiting everything once. So we have here not smaller equal, we have equality. That's the end of the proof. But you correctly understood that there is something important about this monotonic chain.
So basically what that means is as you increase the x, you also increase the y. Mm-hmm. But if we like kind of pause for this moment for a bit and think about the idea of longest increasing subsequence, maybe just on an array of numbers, if we sort all of the points by x coordinate, we might have ties in x coordinate, but I'm not going to think about that for a minute. Then as we go to the right, we basically have an array where the array is just all of the y coordinates. Mm-hmm. So let's say we find the longest increasing subsequence. If that is 500 or more, then we're set.
Yes.
But if it's not 500 or more, we could remove all of those.
I will remind everybody the limits. The number of points is 300,000, k is 500.
I see. Well, 300,000 is bigger than 500 squared, right?
Correct. And
that's what I'm going to end up using.
K greater equals square root of n.
So if we find the longest increasing subsequence, if we can use that, we will. But if we can't, I think that means we just want to find the longest decreasing subsequence. Mm-hmm. And you can prove by just like finding the longest decreasing subsequence a bunch of times that the longest decreasing subsequence will be bigger than square root n.
That's a correct solution for the path version. I will reiterate this, that we, let's say, sweep from left to right. So it means we sorted points by x coordinate. For every point we care about y coordinate. And now we want an increasing sequence, so monotonic chain of points. Every next point is more to the right and more to the top. And here, if we have a sort and we have y coordinates we meet as we go from left to right are 5, 2, 20, 10, 4, and so on. In this sequence of y coordinates, I'm looking for increasing subsequence. And this way I will find a chain, and I know that I can just connect them like this. It is possible that longest increasing subsequence is short, in particular if the sequence is just decreasing or almost decreasing, like 10, 8, 9, 7, 6, the longest increasing subsequence will be very short. But this corresponds to this drawing, and there is a long decreasing subsequence. Maybe in a moment we'll get back to the proof of this fact, but it is true that this is greater or equal square root of n, or longest decreasing subsequence is greater or equal square root of n. And in very short, one proof is about algorithm to find this. We have some number of buckets, each of them is decreasing, but the last element of every bucket creates increasing sequence, and it's that either the number of buckets is big or one bucket is big. That's your basic algorithm for LIS. We'll get back to another proof later. What about a cycle?
What did you say? What about the cycle?
Yes.
Oh, yeah. We have the cycle issue.
Vertex 1.
So, yeah, that's a good point. Well, what if we pick two of them? If we pick two different increasing subsequences, is it guaranteed that you'll want to take one and then take the other?
I think they would need to be far away from each other.
And that's a sketchy condition to require.
Yes, they can arbitrarily intersect as well. Maybe you could modify the way you find it in order to make them disjoint in some way.
Oh, hang on. What if we do an increasing subsequence and then a decreasing subsequence?
One of them can be short.
One of them can be, yes. But we just care about the sum of the lengths.
But what if...
Oh, but if we have just, it could just be all increasing then.
Yeah.
Yes, that's not helpful.
I think that would be a good subtask in IOI, in any Olympiad problem. What if the input is already monotonic? What if the input is monotonic chain, every next x and y are bigger than previous? In particular, this is possible.
Yeah, it's a good question.
And you remember
Well,
this shape, this shape.
I do.
There is something into this drawing. This slide, which we had a long time ago, like 20 minutes ago, kind of describes the solution.
Well, the dotted line, I guess, is very suspicious.
Actually, the dotted line is a red herring. It isn't correct to say that everything above some line is, one side, everything below is the other side.
Okay. Well,
but I will tell you how the optimal cycle generally looks like. It doesn't have to be so nice. Let's say this is possible.
So obviously it's not self-intersecting.
Yes. But it will have two sides, like upper and lower.
Sure. There are multiple ways of doing that too, though, right?
Mm-hmm.
Like just the requirement that it has two sides doesn't uniquely determine what it looks like.
Correct. This could be a problem in itself.
Oh, it does. It does, though. If you keep it monotonic.
I see some similarity to joining points. If you already, to the problem we discussed in your channel, if we already decided something, then the next point, we don't know where it should go without knowing the future. We don't know if we should connect like this, because maybe in a moment we will have point here and this would cross, or like all the points will be here. But this is, here we have two possibilities to connect.
Yeah, so you could, I guess, if you wanted to do a DP, then your state could be what are the previous two positions. So you could store what's like the left row, I guess, and what's the right row. And then you could just try connecting both of them to the next point. So your transition would be order 2.
Yes.
Okay. So you have to, do you have to like pre-compute? I guess it'd just be n cubed, right? The DP would be n cubed because you just have to check all third points.
It's enough to check the next one. I will show you what I mean. Let's say this, I and j. If we say that j is further, then from ij, we move to ij plus 1, or we move to j plus 1j. When we know that one side is up to... I'm doing something wrong here.
Oh, I suppose it's not really monotonic.
Yeah.
Or it is.
I just need to shift this a bit up. This problem becomes hard if we want to forbid intersections, because we would need to check something here. Fortunately, we don't need that. There was no condition about no intersections, and anyway, optimal cycle will not have any intersection.
Okay, makes sense.
So when we are at ij, we can just transition by either considering this new edge, and now we are at ij plus 1, or we consider this edge, and we are at j plus 1.
Even if you did need to consider intersections, it would only be n cubed, right? So it still probably would run in time.
Yeah, because we would need to consider this segment. just let's remember that the number of chosen points is k, so we have k squared. This is k squared.
K squared for the dp. Okay,
yeah. The interesting fact is that k was chosen as to be around square root of n. So really the complexity is square root of n square, so it's just linear, even though we have a quadratic dp.
Sure, yeah, that's very cool. It's a really cool problem. I really like the idea. Like there are a lot of discrete steps in it. Like first you have to make this observation, then this one. And like this certainly isn't, if I were doing this in contest, I might get to the fact like, oh, you can do this monotonic chain. But it's like it's an entirely separate thing from saying, okay, well, monotonic chains are useful to how do I solve it on a monotonic chain? So I think that's really cool.
I'm glad you like the problem, especially because we chose something you didn't know in advance, so it was a gamble. Yeah, quick summary: we were given n points. By sorting from left to right, we try to find a long increasing monotonic chain, like increasing from going from left to right. If that's impossible to find, then for sure there is a long decreasing subsequence, and it can be proved that one of them is at least square root of n, and that's greater than k. And then we do this dp. We can imagine that there are two people, like I don't know, like David and Camille start here. They start both in this vertex. They need to visit all the cities and get at the end to here. Both of them need to get to the last point. They need to visit all red points. And then it's just about trying to create such a path for them. And we iterate like from left to right, and we always know if I'm right now here, then where is the other person? And now which one of us will get to the next city?
So just like an n squared dp from there once you have your monotonic chain that's long enough?
Yes, the total complexity is n log n for finding increasing or decreasing subsequence plus k square, where k is basically square root of n. So you can call that n log n in total. And regarding the proof of longest increasing subsequence or decreasing subsequence, there is a theorem with complicated name. I will put the image on the screen, like Ergos Shakira, I don't know. But one cool proof I learned, other than analyzing the algorithm, is the following. If you have a sequence, and this is sequence of numbers, 7, 2, 4, and so on, and for every position, you write down what is the longest increasing and decreasing subsequence ending here. Like here, maybe longest increasing would be 3 and decreasing would be 2, because this is number 5. There is 2, 4, 5, there is 7, 5 decreasing. Then maybe you see why it cannot happen. Then this is again the same pair of numbers. The
second one could just build off the first one.
Yes, if this is a smaller number like 3, then there is longer decreasing subsequence. So the second number is at least 3. If this is bigger number, then we can expand this increasing subsequence of length 3 ending here into that. And indeed, this cannot be the same pair. So do you see what does it mean for the whole lemma?
Well, it means that you, like if you're going to put a pigeonhole, put each of these different pairs into a pigeonhole, you're going to need at least square root of n by square root of n.
Indeed. We have n distinct pairs, a comma b, with those two numbers being positive, and then if each of those is at least at most square root of n, each of those is at most square root of n, then in total we have at most n. I mean, it cannot be lower than that. Swistak told me today this proof, and I very much like it, or yesterday. This was 7.
Yeah, it's a really cool proof. I like it.
I like it too.
Awesome. Well, unless there's anything else, thank you very much for having me as a guest, Errichto, or Camille. And it was a fun problem. I enjoyed it. So thank you for the opportunity to solve it live in front of you.
You're
Get some help along the way.
You're more than welcome, and we'll do something like that again, I think in around a week, we'll see. Make sure to check out the video on SecondThread's channel as well. I think we should post it on the same day.
Sounds good.
Next time we will mix things a little bit. On David's channel, we will do something like today we did on my channel, the parade. Again, it will be some my problem. And on my channel, we will do something maybe I didn't know, and I will try to solve a problem. So thank you for joining me, and good night, everybody. Thanks for watching. Bye-bye.